Hello students, today we will learn the topic the diode current equation and the diode resistances. In this session we will cover the following contents. First we will learn about the diode current equation which relates the current flowing through the diode and the voltage across the diode. Then we will learn the VI characteristics of the PN junction diode mathematically using this diode current equation. Then we will see the effect of the temperature on the three parameters, that is barrier potential, second is reverse saturation current, and the VI characteristics of the PN junction diode. Also we will cover the diode resistances which are of two types, static resistances and the dynamic resistance. We will also derive the relationship for the dynamic resistance RD. Let's discuss the diode current equation for the PN junction diode. Diode current equation is the mathematical relationship between the diode current and the voltage across the diode. It is nonlinear in nature, and we will see with the diode current equation it is exponential in nature. Also this equation is temperature dependent. So let's start with the diode current equation. This is the diode current equation we have. ID is equals to I naught e की power Vd upon eta Vt minus 1, where ID denotes the net diode current, Vd denotes the voltage across the diode, I naught is the reverse leakage current or the reverse saturation current which is in the range of the microampere or nanoampere. Eta is the semiconductor constant which is taken as 1 for the germanium and 2 for the silicon, and Vt is called as the thermal voltage. It is defined as the ratio of the Kt by Q, where K is your Boltzmann constant, Q is the electronic charge, and T is the absolute temperature. So if you want to calculate the value of the thermal voltage at room temperature, you can put the Boltzmann constant value and the electronic charge value and the temperature in the Kelvin, 300 Kelvin. You will get the value approximately thermal voltage as 26 millivolt. Let's discuss one problem statement based on the diode current equation. This is the problem statement we have. Assume silicon diode with reverse saturation current of 2 microampere is kept at room temperature, has been applied with the forward and reverse voltage of 0.75 volt. Calculate the diode current for the each case. So let's discuss the solution. We have given the temperature as 300 Kelvin. In centigrade, it is 27 degree centigrade. When you add 273, you will get the temperature in Kelvin. So reverse saturation current is given as 2 microampere. So 2 into 10 to the minus 6 ampere is equals to I naught. Then silicon diode is given. So the semiconductor constant is 2 for silicon diode. And at the room temperature, we have already calculated the value of the thermal voltage in previous slide. That is equals to 26 millivolt. So substitute the all values in the diode current equation. So let us start calculating the diode current for the first case when the forward voltage is plus 0.75 volt. So I naught is taken as 2 into 10 to the minus 6 ampere, Vd is plus 0.75, eta is 2, and Vt is 26 millivolt. So you will get the value of the forward current as 3.672 milliampere. Try yourself also and verify the result. Let's discuss the second case when the reverse voltage is 0.75 volt. This is the reverse voltage we have. Vd is equals to minus 0.75 volt. All the values will remain same in this diode current equation except the voltage Vd, where it has been written as the minus 0.75 volt. You can see you will get a reverse current as the minus 1.99 microampere. Please verify this result also. And you can also observe one thing, that there will be no percentage change in the saturation current. You can see the saturation current is I naught is 2 microampere. So it is and the current flowing at the minus 0.75 volt is minus 1.99 microampere. So there is very little change in the current almost. So I naught is almost constant in reverse bias voltage. Let's relate the diode current equation with the VI characteristics of the diode mathematically. We have the current equation as ID is equals to I naught e की power Vd upon eta Vt minus 1. So just multiply by both the terms by I naught. We will get the expression ID is equals to I naught e की power Vd upon eta Vt minus I naught. Now in this expression you have the two terms, I naught e की power beta Et is as the first term and minus I naught as a second term. Let's take the first case when the forward voltage is applied, that is Vd is taken as the positive. So first term will dominate over the second term, as ID e की power Vd upon eta Et is much greater than the value of reverse saturation current, that is I naught. right? So we can write it as a ID is equals to approximately as I naught e की power Vd upon eta Vt. So you can clearly see that in forward bias condition, it will follow the exponentially graph. Your current will rise exponentially. So you can easily ignore the second term. So you will get the characteristics, diode characteristics like this. Now let's take the second case. In reverse voltage is now Vd is negative when the diode is subjected to the reverse voltage. So now the second term will dominate over the first term. So I naught will become much more than the I naught e की power minus Vd upon eta Vt. So Id is equals to minus of I naught. You can see it is the approximate relationship in the reverse bias condition. So this is the you can see this is the highlighted portion where ID is equals to minus I naught before the breakdown voltage. So this is the mathematical relationship between the diode current equation and the diode VI characteristics. Now let's see the effect of the temperature on the three parameters. First, barrier potential we will take. We have seen that the rate of change of the barrier potential can be given as delta V upon delta T is equals to minus 2.5 millivolt per degree centigrade. This expression is telling me that for every 1 degree rise of the temperature, the barrier potential will be decreased by minus 2.5 millivolt. So, what is the reason behind this expression? As the covalent bond will be break due to the increase in temperature, more thermally electron hole pair will generate and compensate the donor and acceptor ions in the depletion region. So, the barrier potential will be decreased, and this rate of decrease of the barrier potential is 2.5 millivolt per degree centigrade. Right. So, let's take the example. If the barrier potential at room temperature is 0.7 volt, so at if we increase 1 degree centigrade temperature, the barrier potential will become 0.6975 volt. It decreases by minus 2.5 millivolt. Or if I decrease the temperature from 27 degree centigrade to 26 degree centigrade, your barrier potential will be increased by 2.5 millivolt. Right? Let's discuss the effect of temperature on reverse saturation current. As soon as the temperature is increased, the covalent bond breaks and it will generate more number of electron hole pairs. This increase in electron hole pair due to increase in temperature will contribute more in the reverse saturation current. Hence, we conclude that as soon as the temperature is increased, the reverse saturation current increases. These two statements relates the reverse saturation current with the temperature. First statement says that for every 10 degree rise in temperature, the saturation current will be doubled, right? So this is the expression from which it is derived. We have the second alternative expression for the reverse saturation current. It says that for every 1 degree rise in temperature, there will be a 7% change in the reverse saturation current. This is how it is related mathematically as I naught T2 is equals to 1.07 delta T into I naught T1, where I naught T1 denotes the reverse saturation current at temperature T1, while I naught T2 denotes the reverse saturation current at temperature T2, and delta T is the difference between these two temperatures T2 minus T1. Let's quickly understand the effect of the temperature on the VI characteristics of the PN junction diode. So I have taken three temperatures T1, T2 and T3, where T3 denotes the highest temperature and T1 denotes the lowest temperature. So this is the VI characteristics we have. Let's plot at temperature T1. This is the forward characteristics and this is your reverse characteristic. Vz denotes the reverse breakdown voltage, while Is denotes your reverse saturation current, which is almost constant up to Vz. So as soon as the temperature is increased, we have seen that the barrier potential has been decreased by the minus 2.5 millivolt. So if the temperature is increased, your barrier potential will be decreased and your curve will be shifted towards the left, right? So now let see the effect of the temperature on the reverse saturation current. We have seen as the temperature will be increased, your reverse saturation current will be increased. So this effect is shown here. As the temperature is increased, your reverse saturation current is going to be increased, right? Now let's see the third effect on the characteristics after the breakdown voltage, that as the temperature will be increased, your reverse breakdown voltage will be increased, right? So this is the overall effect of the temperature on the VI characteristics. Let's discuss the important concept of diode resistances. There are two types of diode resistances. First is called as its static resistance or the DC resistance. Another type of diode resistance is called as the dynamic resistance or the AC resistance. So let's discuss the first, the static resistance. So static resistance is the resistance offered by the diode when the static conditions are established across the diode. So this is the diode we have in which the diode is connected with the static DC source. Voltage source is there. So this static DC voltage source is responsible for establishing the constant voltage and current across this diode. As soon as this DC source is connected to this network, the voltage and current across the diode is not going to be changed. So the resistance offered in this situation is called as the static resistance. So static resistance is nothing, it is the resistance offered by the diode when the DC current flowing through the diode with the help of the DC input voltage. So this is the simple expression for the static resistance as it is the ratio of the voltage across the diode to the current flowing through the diode. If we locate this point on the VI characteristics, this is the VI characteristics of the PN junction diode, and the forward bias characteristic for the voltage across the diode, we have get the constant current through the diode. So this is the point on the graph called as the Q point or the static point, because this point is not going to be changed as long as the input supply is fixed. So this is also called as the DC point, bias point, and by operating point. Operating point, why it is called? Because these voltage will establish a certain operating condition across the diode, which is not going to change, which are static in nature, right? So let's take the example. For example, if the current flowing through the diode is taken as 2 milliampere and the voltage across the diode is 0.5 volt due to the some DC source connected to the diode, then the static resistance will be calculated simply as the ratio of uh, zero point 0.5 volt upon 2 milliampere, that is equals to 250 ohm, right? So in the reverse bias condition, if we talk about that is the diode current is flowing in the range of microampere. So simply the static resistance is minus 5 volt upon minus 1 microampere, which will be comes out to be 5 mega ohm. As you can compare that in the forward region, the diode will offer a very low resistance, while in reverse bias region, it will offer a very high resistance in the order of the mega ohm. After understanding the static resistance, let's discuss the another category of the diode resistance called as the dynamic resistance. So dynamic resistance is the resistance offered by the diode when the AC current flowing through the diode is changing due to the input AC voltage. So this is the diode and it is connected to the AC supply. This AC supply is providing a range of the input voltage, which is now not a static in nature, it is not constant in nature. So due to the non-static nature or due to the changing nature of this input AC voltage, the voltage across the diode and the current, that is delta VD or delta ID, both parameters are going to change with the time. They are not static in nature, right? So if we talk in terms of the VI characteristics, this is the Q point, right? So if the voltage across the diode is changing between these two extreme points, the current is also going to change, right? So for if the voltage across the diode is going to increase in the first half, you can see that there is an increase in the diode current, and if the voltage across the diode is going to decrease, the current across the diode is decrease. So this is the range, extreme range of the voltage with respect to, this is the range for the current across the diode. So dynamic resistance is given as the ratio of the change in the voltage across the diode to the change in the current through the diode. From the graph, it can be easily calculated that the dynamic resistance is also given by this inverse of the slope of the VI characteristics. For example, suppose the current which is flowing through the diode is changing, it is delta ID is equals to 10 milliampere, and suppose the voltage is varying between 0.7 volt and 0.69 volt. So delta VD is equals to difference of these two extremes, that is 0.02 volt. So for these values, the dynamic resistance can be given as the ratio is 0.02 volt upon 10 milliampere, which is comes out to be 2 ohm. You can see it is very low resistance in the forward bias region. Let's drive the mathematical relation for the dynamic resistance using the diode equation. So we know already the diode equation is given as ID is equals to I naught e की power Vd upon eta Vt minus 1, where I naught denotes the reverse saturation current, Vd denotes the voltage across the diode, eta denotes the semiconductor constant, which is 1 for germanium and 2 for silicon. Vt denotes the thermal voltage, which is the ratio of the given as Vt is equals to Kt by Q, where K is the Boltzmann constant, T is the absolute temperature, and Q is the electronic charge. And the value of the thermal voltage at the room temperature is 26 millivolt. So just multiply this I naught, you will get the expression ID equals to I naught into e की power Vd upon eta Vt minus I naught. So already we know that the dynamic resistance is given as the ratio of the change in the voltage to the change in the current, right? So take it reciprocal here. So we can define 1 upon Rd as the delta ID upon delta Vt. That is we are partially differentiating the diode current with respect to the Vd, keeping all other the parameters as constant. What are those parameters? I naught is constant, eta is constant, and the Vt, that is thermal voltage, is also treating as a constant. So just substitute this expression for the ID here. You will get delta upon delta Vt is equals to I naught e की power Vd upon eta Vt minus I naught. So just treat the I naught, eta, and Vt as a constant and just differentiate it. You will get the expression 1 upon Rd is equals to I naught into e की power Vd upon eta Vt divided by whole eta Vt minus 0. Just you can write this, substitute this numerator I naught e की power Vd upon eta Vt, like it will be Id plus I naught, right? So Id plus I naught can be written as I naught e की power Vd upon eta Vt. From this expression you can easily relate this. So just replace the numerator here. So 1 upon Rd equals to Id plus I naught upon eta Vt. So just take it reciprocal, you will get the value of the Rd. That is, you will have the expression for the dynamic resistance as Rd equals to eta Vt upon Id plus I naught. So remember this, this is the exact expression for the dynamic resistance. Let's approximate it for the semiconductor constant value 1 and at the room temperature. So at room temperature Vt is 26 millivolt, put the eta is equals to 1. So at room temperature the dynamic resistance can be given as approximately as 26 millivolt upon the diode current, that is Id. So this is the mathematical expression for the dynamic resistance. Hope you enjoyed this session and learned something. Thank you very much.